Great. So welcome, everyone. Thank you for joining today's CSML seminar talk. Today, we have the great pleasure to host Ting Chen. Ting is a research scientist at Google Brain and obtained his PhD degree in computer science at UCLA. His research interests involve representation learning, generative modeling, discrete structures such as graphs, and efficient modeling. Ting has published very popular work in machine learning. Among other work, he's the first author of SimCLR, a simple framework for contrastive learning, SimCLR version 2, big self-supervised models are strong semi-supervised learners, as well as task-guided and path-augmented heterogeneous network embedding for author identification. Today, he will talk about his more recent research projects in self-supervised learning. Welcome to the stage, Ting, and thank you for being here.
Thank you very much for the invitation. So should we get started?
Sounds good, yeah.
Okay, so today I'm going to talk about the self-supervised visual representation learning. And here is the outline of the talk. Basically, I will quickly give some overview of self-supervised learning and then go into introduction of contrastive learning, and in particular, what matters in contrastive learning and how to do better with a few labels. And then at the end, I'm going to touch upon these potential limitations encountered in current research in contrastive learning. So, the first part is going to be a quick overview. So as many of you already know, that self-supervised representation learning is very important, and it has been made a huge impact in natural language processing and so on. So, you take some unlabeled data like images, then you train the network on it. And then after that, you transfer this pre-trained network to, various of downstream applications. And I would say like there are mainly two categories, rough categories of unsupervised learning or self-supervised learning. The first one is so-called generative modeling of the data, where you generate or otherwise model the pixels in the input space, like autoencoder, GANs. In particular, let's look at this IGPT work that I highlighted here, where they basically train either autoregressive or BERT model on the pixel space, which works pretty well. But there is an issue of like, generation can be computationally expensive, and generating images of high fidelity might not be necessary for learning useful representations. But nevertheless, they work this quite well with a large model and enough compute. And then there is a second category of self-supervised or unsupervised learning, which is like so-called discriminative model. But basically what you do is you train the network to do some pre-test task, both input and labels are derived from, unlabeled data sets. So a lot of those pre-test tasks are quite heuristic based. As you can see, like colorization or predicting two random patches selected from the image, like their relative patch location, and solving some jigsaw puzzles, for example. And then like this one I highlighted here is a pretty simple pre-test task that people found, quite yield quite good results, which is that you take image and then you rotate it in 4 different degrees, creating a 4-class classification problem for the model. And then basically you take some network and then produce like the rotated degree in one of the 4 choices. As you can see, this kind of task, they involve a lot of heuristic, and the assumption is quite ad hoc and might be limiting, when you're treating other images that's, rotation invariant or something else, that it might not work. So here comes the contrastive learning, which I would say more belongs to the second category. And well, so the way I'm thinking about contrastive learning and this line of work is basically, you rather than make prediction in a data space, you make prediction in latent space. So I guess a lot of people might agree or might not agree, but I think intelligence can be somehow equivalent to the ability to predict various of things. I think these are stolen from Yana Kuhn's slides, predicting the future from the past. You can construct different kind of prediction tasks, and then you want an intelligent system to make good predictions. But like maybe we don't want to predict the raw input because they are just too many details that you don't necessarily care about. So prediction in the abstract states seems to be a quite a good alternative. But then you encounter this collapse issue, right? So this is a plot from CPC, like you take the past states and predict the future states. And if the model, train a model to predict these future states, the model can easily solve it by mapping everything to constant, because that's maximize the predictability. So, but there's nothing learned there. So to avoid this collapse issue, I think contrast loss has come into play an important role, where you pull together some positive states which can cause collapse, but you also push away some negative states, kind of preventing the collapse issue. But then, contrastive loss can avoid collapse, but now you still have a question like, what do you predict, right? Because you can predict so many things. Historically, there is this multi-field agreement prediction task, like formulated in different work and in different kind of instantiation, like this predicting the instance identity, like basically treating each instance as a class. So this has been done in 2014 and so on. And then there is also like predicting other views of the same example. I think dating back to 92, where having this maximized agreement on some strip kind of data, and more recent work on different channels of images, and even for this clip, which is if you treat image and the test as different views. So in Sinclair, what I'm going to introduce now is a specific way of realizing this idea of maximize agreement of representation under data transformation. And we're going to use a contrastive loss in the latent space or feature space. So basically this is the kind of the framework that we introduced. So let me go over each of the components. But before that, is there any question? Just want to pause a little bit to see about whatever I have said so far. Okay, maybe we can go on. So in Sinclair, so you can see like we have a data point, and then we make two augmentations, and then we go over some encoder and to get a representation, and then we have projection head mapping into some latent space where we measure the agreement. So let me go over each of the component here. I missed this one, sorry. So the first one is the data augmentation. So in Sinclair, we use random crop and color distortion as two major augmentation, but there are something else like random flip, which is smaller augmentation. And as you can see here, the left top, the most leftmost column is the original image. And if you make random crops and the color distortion, that's like the remaining columns are the resulting, images from the augmentation, as you can see. And then we use a ResNet, but it can be anything else in this work to do the feature encoding. And after the feature encoding, we put additional MLP network on top to project it into a latent space where we define this, agreement. So how do we define the agreement? So basically here, this agreement can be defined using a contrastive loss through the contrastive task. So what exactly is a contrastive task? basically you are given like a set with like two different example, xi and xj are positive. So the task is that you identify xj in the whole set given xi. So as a concrete example, you take original image, you already suppose you already make two random crop, creating two views. And then also like there are some candidate examples from other images in the mini batch. And then you basically take, let's say, this crop and say, okay, among all the potential patches or augmented views, which is the positive? And then because you created the other view, so you know this is positive and the others are negative. This is essentially a multi-class classification problem. So you can use a cross entropy loss basically, as you can see here. So the denominator, so the upper part here is like the positive one, and then the other here is all the potential examples in the set. And something worth noticing is that we use a normalized, we first normalize the vector before doing the dot product, which correspond to a cosine similarity. And then we also scale it by a temperature. And this is going to be tuned. And we will discuss the importance of tuning this temperature. I see something in the chat. Let me. Oh, so Freddie asked, so a lot of pretext tasks are quite making some ad hoc assumption, and how is data augmentation not ad hoc? Yeah, I think that's a fair point. So basically, the data augmentation that you use is kind of like based on some assumption, which we will discuss later. But then how do you, like, can you add new, so I think the framework here is that you can add youth augmentation that you want to train a model to be invariant or to learn some common feature among different views. And yeah, so it still is subject to like which augmentation you use and how you create two views that could make a model kind of subject to some kind of limitation, which we will discuss in the final part of the talk. Okay, any other questions so far? If not, then we continue. So yeah, so basically, as you can see, it's a quite simple algorithm where it's summarizing a small pseudocode. And if you look at this visualization, you can see, it's pretty, so you take a mini batch of images, and then for each image, you do two augmentations. And for each augmented image, you go over some ConvNet or some DeepNet to get the representation. And then the representation is fed into the MLP to project into some space where you define this contrastive loss. Okay, so in Sinclair, it use images in the same mini batch as negative examples. So the batch size and the number of negative examples are tight. And now Moco kind of quite nicely decouple the batch size and the negative examples by introducing a momentum encoder and the queue of negative activations. So I'm not going to go into detail, but the issue that they try to tackle is that how do you get like larger number of negatives when you have a smaller batch size? And they can achieve so by using a momentum encoder and a queue of activations. And then there's also a more kind of progressive way of doing that, which is like you don't even need negative examples, as in like BYOL. When I show is that if you using this kind of momentum encoder with an additional predictor, then you don't even need to maintain like negative examples. You just make kind of this prediction loss in the latent space without collapsing. Also, other than these two kind of ways, there are a bunch of other things, other ways to avoid collapse, not using contrastive learning, contrastive laws per se, but they somehow all use these, some kind of batch statistics, like correlation of features in borrow twin and some kind of, different kind of batch statistics. And I would say like even for BYOL is kind of implicitly doing contrastive learning, but it's still unclear how exactly what exact property of that would be. Okay, so before moving on to what matters in contrastive learning, is there any questions? Just checking. Okay, I see one question. So the question is, why does Sinclair need large batch sizes? Yeah, so larger batch size is for two reasons. So one is that you want the training to be faster, especially when you scale up this training, you want it to train fast, like GPT, like I think the biggest model is nearly a million batch size or something like that. And that, speed up training. And the other thing is for contrastive learning, because the number of negatives kind of is in the objective you optimize, and arguably you want larger number of negatives. So you can contrast it with small things. And then, yeah, for that reason, you also want a large batch size. But we will discuss about the impact of batch size in the next part. So the second question is, what is the importance of G? Why can G is the projection head? Why can similarity calculated on H itself? Yeah, I think it's a good question. I'm going to discuss this also in the next section, like the importance of a projection head. Okay, the third question, how do you design the number of classes? So the number of classes is basically the number of negatives in the mini batch, because I'm saying it as a multi-class classification problem, but you don't really have labels in the training. You just do a task, which is select the positive pair out of the negatives. So negative are so the total number of classes equal to total number of examples in the mini batch. Okay. All right, let's move on. What matters in contrastive learning? So let's first set up an evaluation protocol. So what we do here is we use ImageNet, but we remove all the labels from the training. So it's unsupervised learning. And then we use 3 evaluation protocols. One is the linear, is to train a linear classifier on the pre-trained learned features. And this is a pretty common evaluation way. But the other way is like you can fine-tune the model on a few labels. So like semi-supervised setup. And the third one is that you can transfer the learned model by fine-tuning on other data sets that you do not see before in pre-training. Okay, we're going to see that. And so let me quickly recap some of the results we achieved in Sinclair. So we basically show this unsupervised learning, unsupervised learned features can rival fully supervised learning features in ImageNet classification, like ResNet 50 here. And then when you get to a bigger model, a ResNet 50 4x, we can actually match the linear eval performance. And that's promising. And then we also look at like 1% or 10% labeled case. And you can see like you achieve quite good results compared to the baseline, like especially compared to the classic AlexNet, we can achieve same performance, but with 100 times less fewer labels. And as for transfer learning, we test on a bunch of transfer learning data sets. And as you can see here, Sinclair learned features can, in either linear eval and fine-tuning cases, you can match or surpass supervised ImageNet pre-training when transferred to these other classification tasks. Okay, I see another question. So Freddie asked, what about works that dispense completely with negative examples? Okay, so I guess this is not directly related to the performance here, but yeah. So for those methods that do not use negative examples directly, they still use some kind of batch statistics, or some what it could be some recent kind of activation statistics to avoid using negative examples. So I argue they still kind of doing some implicit contrastive learning to prevent collapse. And in their case, there is no classification loss per se. Like it's more like a regression in the latent space. Okay. Okay, so we also have this case study where you take some image from ImageNet. I think it's validation set, and on the top on the leftmost column, and then search the nearest neighbors. And as you can see, it finds quite similar images as nearest neighbors, which means they learn good features. Okay, so now that if you are convinced they can get quite good results, then let's ask this question: what really matters? And one thing we find is that the data augmentation is critical. So to do that, we study a bunch of data augmentations in Sinclair. And as you can see here, it includes like crop, resize, distortion, rotation, cutout, Gaussian noise, sober filtering. So due to the interest of time, let's skip this part. So just to bring the conclusion here. So this is a heat map where in the diagonal, we apply a composition of two augmentations. And in off diagonal, you have only a single, on diagonal is a single augmentation applied. And off diagonal, you have a combination of two augmentation applied. So you can see first, like on diagonal, the performance is pretty poor. Linear eval is like quite poor. And then off diagonal, you have this entry that's kind of doing much better than all the rest. So, I mean, if you just search around diagonal, you might not be excited about the results, but if you search around this one, you can see it's pretty good. And what is this combination? You have random crop and the color. So I'm going to explain random crop a bit in the next slide, but why color is so important. What we find is that if you just do random crop of the image and compare their color histogram, this is what you get without color distortion. So you have two images and you take 4 random crop from each images. You can see the color statistics are quite similar in terms of the histogram. And if you apply the color distortion, then you can see they are quite different. So if they are very similar, then you can distinguish this image from this image, right? The image in the first row and the second row. They can be easily distinguished by just looking or matching the color statistics, which is not the feature that you want to learn, or at least not all features that you want to learn. So random crop, which is the other important piece here, makes more sense because if you sample random crop like A and B, then you're basically mimicking a kind of prediction task of global and a local view. Like I'm seeing A, what's the more global view would be look like. And I'm seeing C, what's the adjacent view would be look like. So I will argue this random crop is a bit more principled way of exploring the feature or some kind of inductive bias in image or in visual world itself, like what's adjacent, what's a bigger view or smaller view of something, right? So yeah, that's another augmentation. Okay, so now let's move on to the second important piece, which is this projection head. So we did some ablation, like if we not using projection head, we just taken the feature, average pooling feature of ResNet. So we use a like identity mapping, which is no projection head. And then we can also use the linear projection head, which people have used before. And then we also like try a deeper, which is nonlinear projection head with additional layer. As you can see here, if you don't use any projection heads, then the performance is here. And if you use linear, it's improved, and nonlinear is further improved. So basically, this shows the importance of the projection head edit. And even if you use the projection head, then it's still better to use the features before the projection head for linear eval rather than output of the projection head. So I think this answers some questions that was asked before. And then I guess there's also a question like why we know it is important, but now why it is important, right? So, and the rough intuition that we had is that, we basically train this model to be invariant. It's not going to be totally invariant to something like random crop, but you try to make it invariant to the augmentation applied to it. So the final features where you define the loss, it might be more invariant to the augmentation. And maybe you don't want that kind of invariance. So just to give an example here. So if you apply rotation as an augmentation, like you take image, you rotate it, and you say they are positive, so they have to be similar in some latent space, right? And then what you do best to accomplish this task is that you just learn the representation to be invariant to orientation, which can be bad for some applications. So here we have a study. If you take the feature out of the projection head, which is the final feature, you define the loss, you get a performance which is almost the same as random guess for predicting the orientation of the image. And if you take the feature before the projection head, you actually maintain a lot of information about this orientation specific thing that you train the model to be invariant to. So you maintain more features, and I think that's the rough intuition that we have. Okay, so the third component is the model size. So I guess nowadays a lot of people already know, you just need to train bigger models, especially with unsupervised learning methods, like in GPT-3, just make it bigger. But in contrastive learning, I think is the same story here. We perform different study on different model size. As you can see, when you increase the model size, well, actually we try different variants of ResNet correspond to different model size. As you increase the model size, generally performance get better. And this line is that, so all the blue dots here are trained only for 300 epochs. And if you train for 1,000 epoch, which is the red line here, and compared to a supervised learning, as you can see, increasing the model size, you get closer and closer to the supervised learning as you pass. I think right now you can even go above this curve of supervised learning, pure supervised learning. And also, one interesting thing we observe in Sinclair V2 paper is that bigger models are also more, label efficient. So if you have a fewer label, in the traditional machine learning, you might think you need to put more regularization by training a smaller model. But actually, especially I think using pre-training and the fine-tuning, the fewer labels, the bigger you should make the model bigger, which is a bit counterintuitive. But let's look at this result here. We have 1%, 10%, or 100% labels from ImageNet. As you can see, when you make the model bigger, the relative improvement on the first figure here for 1% is much bigger than the 100%. Although, there is also a ceiling effect, like if you have more labels, performance is already pretty good. But we can also look at the absolute top one accuracy. So let's say you only have 1% of labels, and then you are allowed to make the model bigger. You jump from here like less than 60% to 70% top one by making the model, almost 10 times bigger, right? And what you arrive 70% is actually above this line, this model here, which is like trained on 10% of the model of the labels. And then if you jump again from, this more 10%, you make this model bigger, you jump to here, which is about the same as, 100%. So to summarize this result, like if you are able to increase the model size by 10x, you can reduce the required labels to achieve a certain accuracy by 10x. So yeah, so that's a finding in the paper. Make the model bigger helps. So, I mean, this wouldn't be a big surprise for people actually training neural network, to tune the hyperparameters. So one thing is like kind of interesting is that in the contrastive laws with softmax cross entropy laws, right? We use the L2 normalization on the features and the temperature, using a temperature to scale it. And then this is kind of not a convention in classification literature. So we kind of carefully study the impact here. Like you can either not using the L2 norm, in which case temperature is going to be absorbed into the logits, so it doesn't matter. And that's kind of the standard setup if you train a supervised model on ImageNet, for example. And then you do the linear eval, it gets like 57 here. Now, if you use the L2 normalization and then you tune the temperature, you can actually get like 7% boost to 64 here. And as you can see, the temperature, the best temperature is not on the, so it's something in the middle. And what's interesting is the best temperature corresponds to the task accuracy. So how good the model pick up the positive among the negatives. It's not the best. So you make the temperature smaller, and then the contrastive task become better, but then the feature learned is actually worse. So that's something quite unique. Okay, I'm getting a question here. So can we understand the result related to the number of classes and bigger models like this with less number of classes in data sets within mini batch? Within a batch, there could be more possibility of the same classes being trained as different classes. I think, yeah, maybe I should explain it better. So 1%, 10%, and 100% is the number of labeled examples. They are going to be sampled. We sampled in a balanced way. Like 1% is 1% of every labeled classes. So you still have the same number of classes rather than just keep 1% of class and then remove everything. Hope that answers the question. Okay, so what you can see here is that we study in the training epochs and the different number of different batch size used to train. So we tune our hyperparameter on a batch size of 4,000 because that's much faster. And then we scale down to like 256, which is longer. But we basically can see here, training longer is helpful, and using bigger batch size is helpful, which is like reasonable, but is actually a lot more helpful than it actually is. So if we tune the hyperparameter more carefully to small batch sizes, which we did later on, what you can see here, like you train different number of epochs and different batch size, you can see the effect of batch size becomes much smaller, sometimes even negligible. So we didn't tune for even smaller, But I think, yeah, the point here is like the hyperparameter tuning is quite important, even for, sometimes it's just harder to tune all the hyperparameters well. But if you do, then the effect of batch size is actually smaller than you expect. So okay, so the next part I'm going to touch on is like, how do you do better with just a few labels? Which is kind of like a semi-supervised learning setup where, in practice, you have a lot of data and most of them are unlabeled, but you are able to label some of them. And then the question is, how can you do best in such a setup? Before going to the approach that we explore, I'd like to highlight like two paradigms of utilizing unlabeled data. So the first one is that what I would call like task agnostic use of unlabeled data. What it means is that when you use the unlabeled, when the model uses the unlabeled data, there's no specific task information there. Like this popular unsupervised pre-training and supervised fine-tuning. When you do the pre-training, obey you use inductive bias in designing the algorithm you do pre-training, but like it doesn't really know the labels that you wanted to train on the supervised fine-tuning part. But there's another paradigm which I would call like task-specific use of unlabeled data. So when you use when the model sees unlabeled data, it uses them as directly as a regularizer. So you know what exactly the task you try to tackle. Some example includes like self-training or pseudo-labeling, or label consistency regularization, where you want the model to be consistent in terms of making predictions, or some other label propagation methods also belong to this category. So in Sinclair, we kind of combine these two paradigms to make the best performant model when you only have a few % of labels. So the method is basically 3-step, which has been somewhat explored in natural language processing. So what you can see here is that the first step is you do the pre-training. In our specific instantiation, we pre-train Sinclair V2 model or Sinclair model on unlabeled data with a big task agnostic convolution net. And then we fine-tune it on a small fraction of data that has class labels. So this part is task agnostic, and then now this part we're going to use the unlabeled data for the second time in a task-specific way. The way we do it is that we take this fine-tuned teacher, what we could call a teacher, and then we label some, unlabeled data, which is, let's say, specific to the domain that you care about. And then you train a task-specific ConvNet, which can be initialized upon the teacher or smaller network on this unlabeled set, given the guidance of the teacher. And that's going to lead to a better model, as we will see in a bit. But let me just make things a bit more clear what I mean by self-training or distillation with unlabeled data. So what we basically do is similar to distillation, but we use the unlabeled data to distill the knowledge. So what you see here, this is the teacher's prediction. So we go over the example in the data set, which are unlabeled. And then we ask the teacher to make a prediction, which is some softmax over some predefined classes. And then we ask the student network to match that distribution to minimize the KL divergence between the teacher's prediction and the student's prediction. So that's basically what we do in the third step. So let's look at how well it performs. So basically, if you just train on labels, you get pretty poor results on ImageNet with 1% or 10%. And then if you add distillation loss on the label only part, is still not very satisfying. Now, what really the big jump is like when you use the unlabeled data sets, to do the distillation or do the, self-training, then you can see a huge improvement in, especially for small percentage, label percentage. So Freddie asked, what about distilling first with unlabeled data from a narrow domain, such as satellite images, and then fine-tuning with labeled data? Well, for the distillation, you need teacher, right? So in here, what we distill is we have a teacher network that you can already make predictions on the specific task. So you have to do the pre-training first and then do the distillation later on. Okay, so let's look at this plot, which show how well the model performs. So if you just do pre-training and the fine-tuning, you get this blue curve on the bottom here. And then if you do self-distillation, which means you distill to a model that's basically the same, but with some small difference in the projection head, you get big improvement, especially for smaller models, which is quite interesting. And then you get this kind of orange curve, and then you take the biggest model that you self-distilled, and then as a teacher distill to all the smaller models, you get this green dotted curve, which is above this supervised learning on 100% labels. Basically, you can get the same performance with 10x less labels. Okay, in terms of comparison to some state of art, when we publish the work, there is a huge improvement in terms of both 1% and 10% labeled case. Okay, due to the interest of time, maybe I should move on to the final part, which is the intriguing property of contrastive learning. So one thing that a lot of people have discussed is, this ImageNet data set is mostly object-centered, like you have a single object in the middle, and that's kind of introduced a data set bias. And then the loss that defined in contrastive learning is per image, right? For each image, you augment it and define a loss. So what if you have multiple objects in the, each of an image, would they still be able to learn well? I think that's the question that we want to kind of study here. And it's not a particularly easy problem to study because you need to consider multiple objects. And so we just go for the simplest possible setup, which is MList. And then you can put a lot of digits on a shared canvas. And you can see here, you got like 4 digits or 16 digits, and it can be well aligned in the canvas or just randomly placed everywhere. And then we treat this is basically a new data set where each image has a lot of objects. And then we're going to train contrastive learning methods, basically Sinclair here. And then we're going to evaluate the model by training linear classifier for each of an image. So for images with a single object as an evaluation. So what we can find, is that actually Sinclair is able to learn quite well. Even multiple digits are present. So as you can see here, so we didn't tune this to the best performance, but it's a decent number in MList, I would say. And so these are all linear eval on a single digit at a time. So basically we can see here is supervised learning do well, of course. And then if you have a lot of digits, actually supervised learning wouldn't do quite well because they are, after all, just 10 classes. And for Sinclair is able to learn quite well with a lot of digits like overlap or not. So that's a good confirmation. And then the other question that we ask here is, because the contrastive learning methods is based on instance, the loss is defined per instance basis. So are they able to learn local features? So this is another concern that's related to this instance-based contrastive learning loss, right? And so to tackle this problem, we take a pre-trained Sinclair model, Sinclair pre-trained ResNet, and we take a middle layer. So in here we take the final layer before the average pooling, and then we do clustering of those features. And we can use different number of clusters. And on these images, as you can see, when you use 2 clusters, you almost find a whole house. And then if you use 4 clusters, you find the ground, you find the, I don't know, these are trees and the skies. And it seems those kind of local features has some good semantic similarities. And this is another example where, if you have 2 clusters, you find the floor, and then 4 cluster, you find, these labels and, the walls, and then also the kind of like the table and then the bookshelves, I think, and windows. So it seems reasonable. So basically what we kind of conclude from this is, although the Sinclair loss is defined per instance based on instances, they can still learn a quite good local features of sub-image level local features. So the other thing we look at is feature suppression in this work of studying the properties of contrastive loss. So one thing we notice in Sinclair is that like this data augmentation is really important, and the reason is like you have these competing features. They are shared among different augmented views. Like this, the figures on the left here, you can see they share the same dot classes and features, and then also the color distribution. By applying the color distortion, then you remove the color distribution features shared, and then you only have the dot classes. And this shouldn't matter if the model is able to learn them all, but it clearly isn't the case, and that like this competing feature can hurt the other, which I would call like feature suppression, because the presence of the color distribution features can suppress the learning of dot classes features. So what we want to do here is like, we want to quantitatively study the impact of feature suppression among the competing features. And to do that, we create different data sets. So the first, we basically have 3 data sets. And the first data set that we create here is like still the multiple MNIST digits, in particular 2 MNIST digits in the image. And then what we're going to do is we're going to increase one of the MNIST digits, the size of it. And in terms of evaluation time, we're still going to take a single digit and then train a linear classifier. And we train it for smaller digit and the bigger digits. And what you can see here in the result here is that when you increase, so the first digit is always going to stay in the same size, and the second image digit, you can increase the size of it. And what's interesting is when you increase the second digit size, the performance, the feature learned from the first digit size, which is smaller, which is the smaller digit, and the performance gets quite poor. Like no matter how you tune the hyperparameters in, let's say, Sinclair, like different temperatures, to a level like is pretty poor, right? Like 40% or 20% if you use a larger temperature, and which is quite similar to a random network for the smaller digits. So this is quite interesting. It shows that if you have a larger objects, they can suppress the learning of the smaller objects, which is quite interesting even for such a simple data sets. So the other data set we test on, we kind of test on is like this. We overlay these MNIST digits on ImageNet images, and then we can control like how many number of unique MNIST digit to use when we overlay them on the ImageNet images. And as you can see, the random crop are on the right hand, on the other column, except the leftmost columns. They always contain some kind of the digit there. So what we find is that when you increase the number of unique MNIST digits, as you can see in the x-axis, the performance of linear eval on the MNIST digits increase, which is not a big surprise. But then the performance of ImageNet linear classification, which is like indicator of how good the learned ImageNet features, learned features with respect to ImageNet classes, they drop quite substantially from more than 60% to like 30% or less than 40%, or even less one, depending on the hyperparameter setup. And one thing we want to mention is adding these digits on the ImageNet images does not destroy any of those class-specific features, because if you train a supervised network on this data set, you will just do really well for ImageNet classifications. So what this shows is that like the easy to learn features, they can largely suppress the other features, like in this case, like ImageNet classes features. So this is kind of similar to the color statistic destroying, like suppressing the features of ImageNet classes, but in the color distortion, in the color feature suppression cases, what you can do is you can add data augmentation to remove the color jittering. But I mean, for this kind of effect, although it's quite artificial, but like it's difficult to think of a good augmentation to remove all this kind of like watermark, right? Okay, so the final data set that we study is also quite simple. That you take some images RGB with RGB channel, and then you add some random bits. You just sample some random integers and append it into the channel, and you're going to replicate this for all pixels. So nothing too complicated to learn, and it's not going to be destroyed by augmentation. So it will remain the same for two views of the same image. And then we ask the question, like, how many bits do you need to add? Basically, the maximum of this random integer that you need to have to kind of destroy contrastive learning. So it turned out you don't need a lot of bits. So, we test on MNIST, CIFAR10, and ImageNet. What you can see is no matter how you tune the hyperparameter, especially the temperature, and also you change the methods like using Sinclair or Moco with bigger negative examples, and also some other batch statistic based contrastive loss. You take like less than 20 bits to kind of completely disable contrastive learning. And what's interesting is if you use a reconstruction based like VAE, is not as bad as contrastive learning with respect to net. So I think, yeah, that's basically all I have. To conclude on the final bits here, what we see as potential limitation or open challenges is like, how do you make the contrastive learning to deal with this feature suppression issue where the learning can saturate at some point, and you can use data augmentation to favor certain set of features than the other, but there are also cases where data augmentation is unclear what data augmentation to use, such as these bigger and smaller objects, also this kind of watermark effects, like how should we deal with that? I think those are very still very open questions. And with that, I think I'm going to stop here and see if there is any questions.
Thank you so much, Ting. This was really an excellent talk. I will stop the recording now and we can then open the floor for questions.
All right.